Trust me, this is there's no such thing as a stupid question. Anyway, so I want to start with this section on correlation to emphasize just to address some of your questions that other people might have. So someone had asked about what the format of the midterm exam. Essentially, you're going to have a set number of questions. I don't have the exact number. I could glance over and take a look, but the point of that is I think you have 90 minutes to an hour. Why don't I just quick check, okay? The point of the midterm exam that I want to emphasize is that it is timed. The questions themselves are finite, and we're not going to give you more questions than you can possibly answer. You could probably finish it earlier. But the types of questions are going to be identical or very, very similar in the format and structure in which they are presented. Namely, they're going to be very close to the questions you have in part 1, right, where you don't do any analysis. But they're also relevant to the questions that you answer in part 2, because in those sections that we review on Monday, even though you're analyzing with code, we give you all the script to do the analysis, and the script itself presents output for you to interpret. So I think of it as a more of a way to, first of all, give you code and material that get you comfortable to R. But for the midterm, for kinesthetic learners, for people who like to type and get involved and get mucking around in the data, like me, perhaps, you get to interpret and understand and explore the output in different ways. But that being said, we give you all the information, and you're going to answer multiple choice questions, and you're going to answer true or false questions. And you may have some write-in questions, but they don't have to be overly precise. And we definitely are not in the service of knocking down points because you're a little bit off, or even quite off because there is such thing as midterm rounding. So that the questions themselves are the formats. It's basically R output questions, R output questions, R output questions. Sometimes there might be back references sort of in a narrative sequence. So if you're going to skip ahead, which might be important if you know that concept, it's still important for you to know and interpret the material. And the reason we do that is have that kind of structure is that this is what the practice of statistics is. It's the interpretation of statistical output. It is the critical thought process that is involved, the application of the concepts. It is not knowing how to, say, create or upload the special code and do more of the technical stuff. How many students are in the class this semester? More than in previous semesters. I think over 150. But that being said, we have basically, I'm curious to know what Peter, as to pose the question. I think it's, I'm sorry, I didn't mean to mention anyone's name, but, oh yeah. So there are quite a few students here. But that being said, we always scale up the, the sections and the availability. So the reason we do that is simply because it's, what do I say? I think with a larger class, you just have more time that you have to give. And yeah, I think it also is a testament to perhaps the importance of this material. But I would hope to think that it is also a testament to the fact that I think the instructor and I agree that most stats courses, well, I don't want to criticize my colleagues. I think too many statistics courses assume way too much from the beginning. And there are very, very smart people who we all start at the same place. I started exactly where you were when you started. We all started at the same place. And I think from seeing and sort of teaching in other environments where I see assumptions being made, because remember, this is almost a language course. That's the way I'd like to think about it. When you teach a language course, you're going to start with some very simple concepts the elemental forms, and then create a system in which you can think. That's why maybe if you hear two statisticians talk, sometimes they don't understand each other because they've used different dialects, but they also make many assumptions about what you know as an audience member. So that's the goal, is essentially, that's why we started off with maybe concepts that many would consider too easy, data types. Well, guess what? Not everyone knows what a variable is, and that's okay. Anyway, that being said, because it is a large course and because there are many students with many different learning styles and interests, I spent most of my time one-on-one with students who have emailed me or contacted me. So if you have questions or concerns, especially because it is a large course, and maybe you're feeling like, oh, you know, you're drifting out there, talk to me. I'll give you my time. This is what I do, and I think it's the advantage of having this kind of course as opposed to a MOOC. This is a socially mediated online course. So talk to me about your interests, I think, is totally relevant, because research is me search, as a good friend of mine had said. So if we go to the midterm, I would be able to give you a list for that, and perhaps I don't have that. I don't have that with me, but I'll double check, and I will make a note of just sort of cueing you for that midterm, because I know a lot of you are busy, a lot of you have schedules. So maybe we can talk about this week on correlation analysis. Okay, thank you for pointing that out. So perhaps, well, there are a couple lessons here, right? First of all, thank you for pointing this out. Maybe there's almost always ambiguity in questions and in research, actually. This isn't a cop-out, by the way. Someone had asked about this mission 4's questions 4 and 7. So question 4, what refers to examining the scatter plot, I believe, right? And then question 7 refers to what would happen between the correlation if you removed a data point. Is that correct, I believe? Those are the two questions. So one is about removing an outlier. Let me bring up the homework and just change a view. We don't have to look at my mug shots. Yes. So yeah, let's look at that. I just want to be sure that that isn't. I think some of these questions were addressed because we spoke about it as a staff, and I think some of them might be on the discussion board already. That being said, if you feel like you've been unfairly punished, then please let me know. But here's a point I do want to make, which is that we strive in this class to be unambiguous about asking questions. But here's the interesting point, is that so many problems, and you will see this in academic research, you'll see this in studies, you'll see this in policy interpretations, so many issues revolve around our ability or inability to ask appropriate questions or ask clear questions. This is also true in survey research. You can now, if you become cynical from, say, public opinion research, you can say it's all about framing the question. I'll do a lot of work on mental health and well-being, and I can tell you there are a lot of things that that are difficult to control, like the weather. You ask people about the weather, and it's so their mental health or their physical health or their dental health. They will self-report lower dental health when the weather is bad, on average, right? Now the point here is, in the context of analyzing and critiquing questions, sometimes it's impossible to escape ambiguity here. And this is, I think, again, I'm going to drive this home. This is why I've spoken with recruiters, and I agree with them. why a liberal, sometimes people with a liberal arts degree might feel like they are not competent or are they able to learn statistics. I've spoken with recruiters at events. One was a French major and who learned programming and now is a programmer. But she talked about how she actually values that because programming language is very precise and persnickety. But our translation of statistics into the world, you know, taking the complexity of the world into the precise language of stats and models, and then retransforming that into a story, that whole translation process from maybe creating the data to analyzing the data and then presenting the data and then having others present the data in journal articles, a lot of that involves ambiguity along the line. And so that some of that is inescapable. So I'm just saying to, not to say just to deal with it, but I'm saying this is you have to sort of, that is, I think, why there are two different strains of thought processes, right? I think I come from a family of engineers where we are very precise, very literal. But I think a lot of statistics and a lot of storytelling is about storytelling, which is more metaphorical and figurative in a way. Okay, so let's go to the problem sets. If I can find it. Yeah, okay, I can find it, of course. And I'm also going to bring up the slide deck too. Sorry, because I think some of these questions and some of these issues might be better addressed by looking at the slide deck. Okay. So let's see if we can get this. I have this saved as a PDF. I'm going to share the assignment. But if you have any questions, feel free to chime in. Okay. I don't like leaning in so far, right? Okay. You should be able to see this. This is a preview. So, shoot, I can't see. Somehow there's like a little, this is what I don't like about some of these. Let me make sure I'm still recording. Okay, good. Okay. Just got a little scared. Ah! Okay. I'm sorry, I have to move something here because there seems to be some sort of other window open. Okay, good, thank you. My apologies, I'll get this as large as possible. No. Okay, you should be able to see not the whole screen, but you should be able to see part of this. We talk about your role, your mission, and then we talk about the data sets. So you're a political scientist. Right? This is an increasingly important role. And in this case, a political scientist is involved in many, many things that overlap with so many of these other disciplines. You are probably noticing it at this point. But I'm going to dig deep into questions 4 and 5. Sorry, 4, and then question 7. So let me zoom in to this right here. So these all are derived from the data set that we had in the class. And you'll see here, the question here for 4 is that you will see a scatter plot below between 2 variables in the state's data set. So these are state level data set. It's a state level data set. That means the rows or the observations are the states. You will see one indicating the percentage of people in that state, or voters rather, who voted for Obama. And that's in the y-axis, so the vertical axis. And in the x-axis, you will see the percentage of smokers within each state. So here we have a scatter plot, right? And we define scatter plots as something that is a graphical representation of what you could say is the association or the covariance or the correlation between two continuous or numeric variables. I say continuous, that's not exactly correct. In this case, you could consider maybe percentages as theoretically continuous, because percentages are, it's on the number line. You know, you can have any percentage. But it's typically between two numerical numbers. So whereas a histogram might represent the distribution of one variable, its central tendency and its spread. Here we're looking at, and that has the measure of variance, right? Here we're looking at covariance. But it also gives you an idea of maybe spread of that distribution too, especially when we talk about simple linear regression next week, which builds on this. But okay, I had presented a game called Guess That Correlation. It's a URL that lets you look at many different kinds of scatter plots that are standardized. So we're asking you, how would you describe this relationship between Obama and voters? And I think there are two parts to this, right? Every relationship has either a, what do you want to say? A positive relationship, or I would say relation, actually. A relationship is technically, this goes back to language. A relationship is something you'd have with a person. And then you have, well, you could say there are three, right? You would have whether or not it's linear, whether or not you can draw a straight line through it, whether or not it's positive, that is whether it has an increasing slope, or negative, whether it has a decreasing slope. And whether it's linear means whether or not it could be best described as something that is approximately according to a linear line. It's a little obvious, I'm using that several times. Then we talk about weakness. Weakness refers to the slope of the line. If you go flat, there's a flat line, there's no relationship. One variable does not tell you anything about the other variable. If it's very strong, then one variable tells you a lot about the other variable. One of the other students had referenced the code that we'd used last week that gives us an idea of how to answer that question, perhaps using other information. That being said, I think you can, well, I would say not I think, but one goal of this course is to actually take data like this and to interpret it. That being said, the caveat is things like moderately strong, moderately weak are not necessarily the best description here. So let's see, I don't want to open another window. Does anyone have the, well, actually I'll look at what the correlation between smokers is. Oh, I see. I apologize. I think the wording is somewhat tricky. Walter, did you get an answer for that? Otherwise, I'll open it up and I can run the code for us. Here. I think I have it listed somewhere. So what I want to point out, and I'm going to zoom in here so we can actually see these individual states, right? We label the states here, which is kind of neat. You can see where your state is. So the correct answer here is, it is negative, and I'm going to annotate here. This is a negative relationship because the slope, sorry, I wanted a straight line. Let's see if I can get us to draw here. Draw. We're going to draw a little straight line here. Okay, good. We're going to do this in red, so it's a little bit easier to see, maybe a little bit thicker. So Yeah, so the correlation is negative 0.33. So that, again, remember though, the correlation doesn't give you the answer about whether or not the association is linear. A correlation assumes that the relationship is linear. That's a very important point here. That's why we always look at the data. We look at the scatter plot. And often, especially I think because of personal interest, corporate interest, private interest, personal or academic interest, or governmental interest, you will not see all of the data. I'm writing a book on state policy and child health outcomes. And typically what I'm doing is I'm scraping the web. I'm actually reanalyzing aggregate level data that are hidden in government documents. Well, that's because, and that requires an interpretation of the data here. So, but the key points here are, it is negative because we have a negative slope. It is roughly linear, we could say. So it's not a nonlinear relationship. It's not curvilinear, right? If you just sort of squint, most of the points will squish here. We could say it's moderately strong. I think as long as you can see there's an association here. Let me see what the options we gave here that might add to the confusion here. This is probably a problem of updating the quizzes so you don't have to write in the answer. So if you notice, all the answers show that it's negative. 2 out of the 4 say it's roughly linear. So remember, we say roughly linear. We're not saying it's a linear relationship. That's a straw man argument. In other words, it's not a linear relationship per se, but it's not nonlinear. And we know that because there is a general relationship there. Now the question is whether this is moderately strong or moderately weak. It's moderately weak. And the reason we would say moderately, well, I said, I'm sorry, moderately strong. Look, if I made a mistake here, I will talk with the instructor and see if I can see what we can do about that. And I'll tell you why. Because strength and weakness, we did technically give you an index of strength and weakness in the lecture slides. So that is a test, I guess, of that knowledge. I slipped and I said weak here because if you recall, I said Monday. It's quite common in social science data to be happy with a correlation of 0.5, for instance. That being said, 0.3 isn't that great. It's not something to boast about. To give you an example, in one of the most controversial books of our time, there were some essentially racists who had said that basically people of color are less intelligent than whites and to a lesser extent East Asians. And they looked at correlations and stuff like that. Well, it was full of faulty social science, but it also also bragged about a correlation or highlighted a correlation of 0.2 between brain size or skull size and intelligence. A correlation of 0.2 for skull size and intelligence led the authors to conclude that men are smarter than women. I think we all know that, trust me, but look for yourselves, the evidence does not show that men are smarter than women and that there's too much noise here in terms of a correlation of 0.2. That being said, we're talking about states, we're talking about different things, and a correlation of 0.3 is a bit larger. So I'm going to talk and see if I can award a point for that if you got it wrong. How many of you got it wrong? Did a few of you get it wrong? Yeah, no, it's our fault. No, well, I don't know if I can get away with this. I'll tell you why. I'm going to give you a new slide here, and that's, we did emphasize this as a rule of thumb. And this is how, if you were in any doubt, this is how I would have answered the question. I'm going to stop the share, and I'm going to do a new share. Look at the wording here. Interpreting correlation of magnitude. Weak to moderate. Now, the answers to the question emphasize moderately weak or moderately strong. Where do you see the word strong? I highlighted those in yellow. So yeah, correlation to 2.2 is very weak. So weak to moderate. 0.2, moderate, it gets closer. These aren't hard and fast rules, and it does depend on the context, I have to say. That being said, I think we probably are going to stay the same on this question. And now my memory is flooding back from previous semesters about this. I just feel very bad for slipping up and saying weak, perhaps because weak only in a relative sense that we kind of want to see compelling evidence, maybe at least 0.5. I sort of talk about 0.5, medium to substantial. Below that, there's greater doubt. And we can see that there should be evidence of greater doubt for this, because I'm going to reshare the problem set. Make sure I got that one. Do we have that? Yep. Okay. If we look at this thing, I'm going to try my best to draw a linear fit line, which basically says if you could describe sort of the general tendency with one line, a linear line, which is what we're going to talk about when we talk about simple linear regression, what would it look like? And basically, you're just trying to sort of fit the line right through most of the data, the one that might characterize the data points mostly. I think that's pretty generous because see, I'm not even happy with that. I think you could say it's probably there, but I'm going to clear it, clear all drawings, and I'm going to draw it one more time. Probably something more like that. Meh, I don't know. The point is, the reason you're not drawing lines to just represent data is because next week we're going to talk about how you actually use statistics and to actually mathematically fit the best line to describe a correlation. And so a best linear fit line in conjunction with a scatter plot gives you what, in essence, is what we're talking about with statistics. A representation of the data, which is the best linear fit line, which is this little blue line here, right? It's sort of like a map of what you might predict if we sampled somebody else or another context or similar context, what you might expect if you know the percentage of smokers and Obama voters. But it doesn't describe the data fully. So it is roughly linear, and I'll tell you why, because we can see some blank spots here, right? We can sort of see, we can see that it's linear because there's nothing right up in this quadrant. Remember, if we talked about correlation, we talked about dividing it into quadrants. These are exclusion zones. Where do we see the data now, huh? Well, we see the data in two places, right? The data actually exists mostly here at the bottom, lower left-hand corner, and then to a lesser extent in the upper right-hand corner. Okay, so, just removing that line shows to you those two boxes are filled. It's a negative relationship. It's roughly linear, and it's not that strong. And it's, sorry, what did we say? It's sort of moderately strong. And it's moderately strong because, you can actually sort of identify a linear relationship there. And in the lecture slides, we gave you sort of a heuristic or a sort of a benchmark here. This is important, though, to keep in mind because despite sort of the relative benchmarks for correlation, it is widely considered what in psychology is referred to as an effect size. Remember, it is standardized. So to the extent that we actually have a sort of a lingua franca among different statisticians, among different fields, correlation is one of the very few measures that we can really use to assess the size of an effect. Say you have an experiment. You can actually translate different kinds of analyses to correlations. And in fact, that's what one of the neatest papers in psychology had shown. It basically transformed every psychological study, social psychology study, over the past 100 years, every finding with all the variety of different statistical models into a correlation between, say, the treatment of an experiment and its outcome. You take each one of those papers, you have a correlation for every paper. And then it looked at the trends in correlations. So, and it interprets correlations for each study. Say I publish a paper, and I say people who say power pose, stand up tall, feel more confident. I worked with a psychologist who actually did that experiment, and that will have not only a difference, a statistical difference, but also a size of how much of a difference in the outcome there is. And that gives, so the power can't be understated of the correlation, because literally you can, maybe you're comparing apples and oranges, but you're also just taking an entire discipline and making it so that you can actually see how large effects are. And what they're finding is once studies are published, it seems like more tend to be statistically significant, but then after the initial publication, it tends to, the effect size tends to decrease. So there is a diminishing effect size in psychology studies. Although more studies are statistically significant. And we'll talk about that in terms of substantive significance, and then also substantive significance, which is like a correlation, as long as it's interpreted correctly. And then statistical significance, which is basically, can it get published? And there's a huge debate. I haven't brought it up because it's not topically relevant, but we will bring it up. And it's about the whole question of the p-value. Very interesting time to be a statistician, because most statisticians are saying we should throw out interpretation or how should I say it? Statistical inference. I would say no, but we'll talk about that later. Don't worry about that. All I'm saying here is we're not really inferring anything. We're just, right now we're describing something. So I'd say in the real world, we can debate about the terms here. Moderately strong, but we can't debate about that is negative. And we really can't debate about the linearity here. If we did, say, a sort of a smoothing plot, this is a locally average weighted plot, it might go something like this, which is sort of like a non-linear thing. Actually, I'm gonna clear all. And that's what we often do in statistics. We might actually weight sort of according to some of these outliers here. That's still roughly linear. I don't care. You're still drawing this little river through the data that can be basically represented also pretty accurately as a rough line, as opposed, and that's, I think that's also represented as a density plot. What would not be linear? Something like this, obviously U-shaped, right? Or something that is maybe inverse U-shaped, right? Or perhaps something that's of big concern within the environmental ecological world, which is this idea of an exponential relationship, right? So the idea is that we might have or logarithmic function, right? So this is like, we might have something that's really low and then goes all the way up here at the top. Excuse my bad penmanship, but linear those are non-linear. Roughly linear, it's pretty undebatable. Moderately strong, yeah, that's a reference to the notes. That being said, I'll look at the number of people who got that wrong and how they got that wrong, and make a decision as to whether that's unfair. But I think because we gave you guidelines in the lectures, maybe we can't budge on that. Maybe half credit, who knows? All right. Any other questions about, I think, now that we're looking at a scatter plot? I'm going to scribble my Bob Ross drawings. Unless you have any questions about interpreting scatter plots. I think it's a nice teachable moment. 1, 2, 3, I'm going to clear it. Okay, good. I do want to say one little thing about this, though. Remember, correlations talk about standardized associations. we're fortunate here because this graph here, they're both measured in the same units. Often we want to standardize the x and the y-axis, so that way their association can maybe be compared across different types of data points or different variables. But that's not really relevant here or there, except when we talk about covariance. Okay, the next question is about question 7. By the way, I appreciate you highlighting particular questions. That way I don't have to go through the easy ones or the ones that maybe don't have as much of an issue. Let's see. What would happen to this correlation if we remove the state with the lowest percentage of smokers from the scatter plot in question 4? Yeah, okay. So there are a couple things here, right? This is where I analyze, which is just a fancy word for breaking things down, and I'll synthesize. And I always focus on this question here. I always focus on the question first. What is exactly meant here? Okay, so we know that it wants to know about how it would describe the correlation. What happens to a correlation when you take or remove outliers? And I know this to be an outlier. This window should be opening. Okay, yeah. Okay, so someone had looked at something about the Spearman correlation analysis. So that's not something we emphasize too much in the class, but the reality is there are actually different kinds of correlations. So there's a guy named Spearman who basically talked about correlations. Yeah, they come up with different statistics, right? So is there something you would like to say with the numbers? What do you think? What do we know about the Spearman correlation? Do we know anything about it? So when we talk about correlation analyses, we're often talking about the Pearson correlation analysis. So you often see this history of sort of using people's, the creators' names, I would say. My alma mater, Kansas State University, for example, had a statistician named, I think, David Cook, and he created a measure called Cook's D, which is, in essence, a measure of an outlier. So Spearman correlation is not a correlation in sort of the traditional sense. It is actually a different measure that is, it can be responsive, and this is not always, this is the problem with, I think, statistics, just sort of ad hoc, just throwing out different kinds of versions. First of all, no correlation is perfect. This is what we have to say. No statistic is perfect. No map of the world, no model is perfect. We use model, by the way, in a very technical sense. It's funny because in French, the word model is mannequin, like a mannequin you see in a store, which is, I think, a good way to remind yourself, what is a mannequin? Well, it's a representation of something. It is not the actual object itself, and there are different ways to construct mannequins, and they can be critiqued. But it all depends on the context. So this, I don't want to say detract from what I want to emphasize in the class, which is that when you talk about correlations, assume you're going to talk about a correlation, a Pearson correlation, which is the assumption of linearity. A Spearman correlation looks like something like a logistic function. It's non-monotonic. Okay, fancy word. Monotonic simply means same. Tonic, I'm not sure what it means. There's same characteristics. In other words, so if something that is monotonic is a straight line. What I showed you was non-linearity is non-monotonicity. So yeah, it might account for some type of non-linearity, but maybe not the non-linearity that was of interest to us. So I just want to make sure I got the Pearson correlation reference correct. Because the name reference, because I don't want that at all to be a measure of confusion. Yeah. And in statistics, we typically refer these with different symbols, or in psychology in particular, because they use a lot of these measures. So an italicized R, it will refer to Pearson. And this is what we're going to talk about. R is a measure of effect size. Equals linear correlation, named after a guy named Carl Pearson. And then rho, the Greek symbol rho, which is sort of like you just look it up, which is how it's represented, equals Spearman correlations. Now, if I looked at the paper and I saw a Spearman correlation, I'd be like, show me I gotta see the data, tell me why you're using this. But the main point is Pearson correlation, Pearson, those names are very correctly. Spearman, in fact, if you look at like the whole concept of effect sizes, standardized units, we call them coefficients because it is actually coefficient. It's actually a standardized measure of how two variables might co-vary, whether or not they're linear. So, and there are a whole variety of them that use Greek symbols. This is why actually I learned a lot more about Greek and learned more about Russian, because Russian is derived from a lot of Greek symbols. It actually helps you to use Greek. But the point is that I'm just looking up to see how many correlation analyses there are, or how many different kinds of correlations we could actually come up with. Well, I don't know. Anyway, the point is, I can look that up later. The point is that correlation is almost 95% of the time is going to be a linear. It's going to be the Pearson R correlation. And when I talk about effect sizes in that context, it was talking about the Pearson correlation as opposed to these other options. But you'll see a proliferation of some of these standardized measures. Don't be betrayed by, don't be confused by those. But there is a whole field called robust statistics. I actually had a great chance to talk with one of them. He's a very opinionated person, but robust statistics are those kinds of measures that attempt to deal with outliers. And this is where we have this thing here. Now, actually, I like this point here, so I'm going to type this in, if you don't mind, because what you did here was actually you provided a statistic that increased our correlation by accounting for potentially outliers. So right here we have this correlation here that attempted to deal with outliers. That's one way to deal with outliers without removing data, but it comes with a cost, which is that there's a certain kind of automaticity if you're just applying a statistic and iterating different kinds of stats to get your correlation higher. And many of these have assumptions that you want to check first before you apply them, because outliers can exist in many different ways in many different forms. That's why I drew 3 or 4 different kinds of nonlinear forms, but I only drew one linear form, right? If you talk about the way that 2 variables are represented. Now, this is slightly higher than our correlation of 0.33, equals sort of a robust statistic. So what that does is it will tend to deal with outliers. Now, outliers, in a general sense, we talked about in a sort of a univariate context, right? We talked about within the context of box plots and within terms of skew, and how they affect measures of central tendency, right? Mean or median. And I mentioned robust statistics there, right? The median is more robust to outliers than the mean. Okay, so actually I'll just clear that for now. But the point is, let's get back to this context here, because while I don't like to throw away data, I'm not a big fan of removing data. It is still important to, as a statistician, to double check your results. We are easily fooled by our own desires as well, right? If I wanted to publish a paper, again, because I'm worried about getting tenure, which happens to the best of us, then I might be motivated to present the correlation that tells the best side of the story. Well, that's going to bite you. It's going to hurt you because you're going to hurt your reputation as someone who's not honest with the data. And also, I think that kind of analysis comes with a sense of discomfort with the data. Learn to love the data no matter how disappointing or surprising the results are, because it's information. It's telling you something. And removing the data points and then seeing what happens to the model, say the association, is also informative. And my advice is you wouldn't present the Spearman or the other one, but you might present what happens to the linear correlation, because it's more common occurrence when you remove an outlier. And then you might say, then I'm going to use a Spearman correlation because of this and this and this, because it addresses this type of nonlinearity. Well, let's go back to this point here, because I think what's most common in practice is to remove the outliers and see what happens. If it reverses your story, then it's not, your story is not going to be very strong, right? It's sort of like if you build a house and you remove one beam, one support, then the house collapses. It's not a strong house. If you remove that beam and there are many other support beams there to keep the house up, well, then you can make a generalization that, okay, this structure is relatively solid. It'll keep us shelter from the storm. And that's what we're kind of doing when we sort of do these verification checks. In other contexts, we would call these actual regression diagnostics. It's a way of telling the story and making it convincing to your reader and also demonstrating your expertise. Okay, enough talking. Okay, so if you remove the state with the lowest percentage of smokers from the scatter plot presented for, so first we have to find, this has a couple layers of meaning here. I remember I talked about interpreting this. As long as you understand this, please chat if you have any questions, or chime in if you have questions about interpreting this. Because we're asking you to identify the state with the lowest percentage of smokers. Which one do you think it might be? I'm going to ask someone to type this in, because I feel like I don't want to answer it. What is the state with the lowest percentage of smokers? That's right. Look at this. And this is where context matters. If you're from the United States, I know even, not even, but say my girlfriend is from Canada, and she wouldn't know this fact. But if you're from the United States, you might be, or maybe if you're even from the East Coast, you might not know this, but I'm from Kansas, and everyone that I knew, by the way, here's Kansas. Everyone from Kansas knows, even though we're geographically quite distant, everyone from Kansas knows that Utah was founded by Mormons who are very abstemious in caffeine, alcohol, and smoking, among other things. It has a very large. There's a very large Mormon, which is a I guess not a sect, a form of Protestantism, of Protestant Christianity, although many Protestants might debate that, but let's just classify it as a form of Protestant Christianity that is that has injunctions against smoking that are quite strong and normative, plus it has a large Mormon population. So here's where context matters, and domain knowledge, right? Because I look at that outlier and I know, okay, the data are somewhat making sense. You might import the data set and you might not know anything that's going on. And by the way, there's Kansas, right? This is also a deeply religious state. It's in the quote unquote Bible Belt, which is also interesting because here you also see Hawaii with fewer smokers, I'm not sure if it's that religious. I don't know much about Hawaii, but politically, it tends to vote very, very democratically, right? So that form of smoking is probably not informed as much by sort of maybe what you might call the Protestant ethic. But there are always exceptions, right? Oklahoma to the south is very high. Now, of course, you might think, oh, I'm just giving a digression here. I'm just sort of emphasizing the point that there's a lot of information packed in a correlation analysis, especially when there are labels here. And so you can use that extra information, especially if you have domain knowledge, as a verification check. So now we want to know what happens when we remove certain data points. But the first thing we had to do was identify it. The second thing we had to do, now what we have to do, is we have to think, what is the relationship with Utah versus everything else in this I guess scatter plot. And I'm going to try to show this with you through a sort of a different different way of sort of showing you what a relationship looks like. And I'll do my best here, because I think a linear line might not explain what this whole swarm actually is, which is kind of. Let's try. I'm gonna try to put a little box here and see if I can spin the box here. Can I spin the box? No. Okay, never mind. Clear my drawing. What I want to show here is I'm just gonna draw. Okay, mouse. I want to sort of give you an idea of what the whole of what the whole association looks like. Yeah. So there's this. I'm just kind of overlapping all of this. Right. So you have some of this here, just so we're kind of looking at this maybe as a cloud of points. One of these things is not like the other, right? So people are looking at other states. Connecticut. Where is Connecticut here? Now that I've erased this, they must be. Oh, yeah. Interesting. So they're low on smokers, typically quite liberal. Same with California. So that's also very interesting with data exploration, right? You might have the same outcome for different observations, but have very different mechanisms, very different forms of explanation. This is why. This is another, I think, value of statistics, is that often in even political discourse, since we're talking as political scientists, you will talk about identity politics, which is sort of, talking about maybe certain categories of people who tend to vote certain ways. And in the United States, we have two parties, right? We have Republicans and Democrats, and we have maybe some third-party candidates. And then we have states that are represented as red states, which are Republican, and the blue states that are more traditionally Democratic. I'm saying this for those of you who might not be aware of sort of American politics. Otherwise, it's sort of pretty obvious. But the point I'm making here is, with every average, there's sort of a tyrannical reduction of the data. And if you when you're reading political discourse or political articles, you might want to think about, well, what are the outliers? What are the exceptions that might be missed when we talk about, well, red states tend to have smokers, and blue states tend to have, Democratic states tend to not have smokers. And then the journalists or editorialists might say, well, it appears that these red state people, these traditional red staters, are moral hypocrites because they talk about responsibility and yet they're engaging in unhealthy behavior. And then you could go on and on. Well, the point here is not only are we conflating people who vote, because there's a lot of heterogeneity in politics within states. There are Democrats in every state. There are Republicans in every state. But we're also misrepresenting the variation or the spread, not of just one variable when we talked about sort of the distribution of one variable, but also when we talk about associations. And you're going to hear that it's going to be difficult to unhear, I think, when you talk about splitting any large heterogeneous population into two groups, those like this, those like that. And then you might want to ask, well, what's the political point here? Blah, blah, blah. And this is where it kind of gets a little difficult, because then it's also easy for the statistician to be to miss these things. That's why it's often, there's an article called, I think, Zen and the Art of Statistics, which is essentially saying we shouldn't just try to publish that are statistically significant results, but take it slow. Be okay, because then that's where discovery happens. So here we have Utah. For political expediency, we're going to circle in red. Okay, so what's going to happen? What is Utah doing to the rest of this group? What's it doing to, say, if we fit a linear line here, this is going to be kind of interesting, but I think also pedagogically useful. We'll fit if I can find a good color, I'll get, I think, a nice black line here. Okay, we got a nice black line. Let's just assume this is our line of linear fits. What will it do if we remove this data point? What is this data point doing, first of all, would be the question. And then you can ask, well, what's it doing? Well, what we're doing when we talk about a correlation is we're talking about how things vary. And remember, when I talked about the correlation, I talked about how two quadrants are basically empty. Unless someone's answering. It skews the mean, and we can talk about that in the univariate context. Someone had answered that, but it lowers the mean of smokers. Both great points, right? It does something, but it doesn't exactly lower the mean, right? Because, well, let me go back to the question to make sure that I'm not missing a point here, because I want to tell more of a story about the scatter plot. We'll go back up, don't worry. Well, what happened to the correlation? Yes. So the answers refer to the mean. This is why it's important to keep this in mind. But however, you're not incorrect here. If we think about this, what we're doing here when we look at the distribution of smokers, if we could sort of, well, I can't really visually show this, but if you could sort of maybe imagine there's no y-axis and just think of this as a univariate distribution of smokers, you're right. Utah is skewing the mean. What's it doing to the mean, the average of smokers? Well, it's decreasing it, right? Americans are going to be, the average American is going to be, the average state levels of smoking is going to be much higher if we remove Utah. So that does tell us something about the mean, and that's correct in this data set, or in this analysis, because we can kind of look at the mean here. We can sort of see what would happen to the mean. Now, what is changing the mean of one variable due to the other? Well, it also changes our association. So if we lower the mean here, what we're going to do is we're actually going to basically, and I'll try to draw sort of a new line, and we'll make this green. What we're gonna have here is, I don't want to draw this too bad, yeah, what this is doing is that if you look at that distance here, I kind of think of like these outliers as kind of a weight on this line. So if you sort of think about it this way, I know it might be a weird analogy to think of, but maybe you might want to think of it as this way. I'm going to draw a little arrow here. This is a big weight. It's an anchor. It's just pulling that thing down. So we're representing the line with everything, including that big outlier that's weighing that correlation down. Right? It's sort of like, so what happens when you take a weight off something? Oh, you feel a lot lighter. And that's what you're doing by removing that outlier of smokers. You're going to see a correlation that's going to be higher, considerably higher, right? Because now, well, I don't want to do that. Well, we'll still do this. Ugh, I don't want an arrow here. I wanted to draw just a regular line. You're going to see a correlation that's going to be, okay, a little bit like that. Now, it's still going to be roughly linear. It's still going to be negative. So the story you're going to have is going to be the same. You can say, well, we're moving Utah. Of course, it is an outlier. seems to suggest that the correlation seems to be a little bit higher. And that's exactly what happened when we use Walter had shown the Spearman correlation, which is a kind of robust statistics. The correlation went from negative 0.33 to negative 0.43. Notice I said correlation higher, because again, when we often talk about correlations, we're talking about the strength of the association. So that's more often than not the case when you hear people talk about correlations. Why? Because a correlation of positive 0.5 has the same strength as a correlation of negative 0.5. And in fact, if you reverse the x and y variables, or you reverse the representation of the data, say you look at the non-smokers, the percentage of non-smokers, you'll have the same, you'll just have the inverse, but you'll have a positive correlation. But the value of the correlation will be the same. So it does give you direction, but direction is also a function of how you present your data. Right? So if this were non-smokers, then you'd see a positive correlation. That's just something I wanted to catch myself there, just in case that's a point of confusion. When I say higher correlation, I'm often talking about strength, because it's so obvious when we talk about positive or negative what the association is. Does that make sense? Yeah, okay. What about if we removed West Virginia? This one right here, we could call that an outlier. Let's say we removed Utah and West Virginia. So now we have this pink line. This is an outlier, right? It's the highest number of smokers, but it's not that much of an outlier, I'd say. Right? This is where the concept of an outlier becomes quite subjective. I'm sorry if I'm not missing everything. Right. So what would happen if we removed West Virginia? Almost heaven, West Virginia, like the John Denver song, right? But what we see is that this is a relatively, we'd probably call this a red state, which is also a misnomer, right? Because it has mostly Obama voters, but I think it's traditionally votes Republican, but also has a high number of smokers for a state that has voted for, tends to vote for Obama. But it doesn't. But for most states, it's not like Oklahoma or I don't know. It tends to vote more. As how I'm going to say it. West Virginia tends to vote more for Obama than one would expect, given what the percentage of smokers are in the data set. That means that it is an outlier, but not a large one, because there tend to be other states that sort of vary quite a bit. And this is why it's roughly linear. Utah is the obvious outlier here. Okay, so the point is outliers are somewhat subjective, but some have a greater influence than others. This is in part by, I would say, there are two attributes. One is their distance from the rest of the pack, right? The other one, assuming we have a linear correlation, the other one is whether or not there are lots of other others that are sort of maybe part of the spread. So West Virginia is somewhat distant, not as distant as Utah. And it also has a couple friends here. It has Pennsylvania, which is kind of close, and Indiana, that's kind of close. You could also say the same thing about Wyoming. Oh, sorry, Idaho. Idaho is Kansas and Wyoming. So I put a blue line there. Sort of, yeah, those are somewhat outliers. They're not well predicted by our statistical model. But it's about distance plus sort of the number of other values here. And that, I think, is why it's actually not inapposite or incorrect for you to actually talk about mean and skew, because this is kind of the two-dimensional version of mean and skew. And unfortunately, in this class, we're going to stay with the two-dimensional world. But when you talk about multiple regression, which we'll have as an option, you're talking about fitting, sort of looking at hyperdimensions, right, which is kind of cool. 3 variables would be, say, x, y, z axis. But when you talk about, say, 50 variables, you're looking at a 50-dimensional hyperplane of variables, and you're trying to look at what hyperplane fits those when you talk about linear regression. That's kind of neat, I think. Okay. That's a lot of talking for that, but I hope it was a better exposition than just going line by line, because part of this is just to sort of clarify what's important here. I think some of these questions I'm going to skip. I know we're a little bit over time, but if there's any other question here. Okay, which state has the highest percentage of votes for Obama, right? Sort of the inverse of the other question. You just look at the y-axis now. Sort of an inverse of looking for, say, the x-axis. It's Hawaii. Do we know why, by the way? Those of you who maybe from the United States might be more familiar with this, but this is also a nice robustness check with domain knowledge. Obama was raised by his Kansas grandparents in Hawaii. His mother, Mary Ann Durham, was actually from Kansas, which actually, yeah, well, you still see a relatively high percentage of Obama voters, but maybe not as high as one might expect. Anyway. But he is from Hawaii, and that might also explain it. But it's also traditionally a quote-unquote blue state, as opposed to, say, I don't know, Kansas, for instance, or Alaska. Okay. We talked about what would happen to the correlation. So yeah, we had this as a writing question, and we're not going to have any writing questions for the final. But we do ask you about this is where I sort of highlighted before, you know, this idea of covariance. Covariance, remember, is a measure of effects, is not a measure of effect size, it's a measure of directionality. I think I'd want to be clear here because we are dealing with units that are the same, so technically you might be able to debate me here. Yeah, I just want to be clear. So covariance, as I keep drilling home, only tells you about the that there's a positive linear relationship. Why do I say positive linear? Because we're not talking about Spearman correlations. We're not talking about robust statistics. We're actually talking about the essence, the foundations behind the standard correlation, the linear correlation, the Pearson correlation. Carl Pearson, by the way, is the person. The Pearson correlation. So we know that it's linear and it's positive, but we can't really conclude that's the strength, because that basically depends on the units of the two variables. That's basically the point here, right? We can't standardize this. That's why you often don't see covariance here, except when I talked about multiple regression, fitting items into hyperplanes. You will talk about covariances between different predictors of an outcome, right? Because here we're only taking one outcome, one couple variables, and we're saying if we know something about smoking, how does that predict Obama voting? When I talk about prediction, I'm using not in the Nate Silver prognostication forecasting term. I'm using the language of statistics, where we're saying where we have a question and we want to answer that question, which is akin to the logic to using conditional probabilities to estimate, say, what the relative risk would be. We're saying conditional on what we might know about one variable, what are we going to see? Even though we've collected those data, even though that already exists, we still haven't seen it technically. So that's important to point out when we talk about prediction. It's a lot of people might not like to use prediction, predictor variables. I kind of like it because it emphasizes your logic of thinking, and also maybe the logic of reasoning and of interpretation and of probability that is so central to stats. So the point I wanted to make, though, is we will, in the way that we think about statistics, is when we talk about predictor variables, we can have many, many predictors. We can only have one outcome that we're going to predict. So like a project, if we wanted to expand on this, we wanted to say, I want to look at the joint predictors of obesity, smoking, and college education on Obama voting. Then you could examine those in a multiple regression context, which we talk about, as I keep, for the third time I've said, we have it as an alternative. And that's sort of statistics that will never leave you. But, and that's also what you will read about in the papers when they say, when we control for or adjust for something, they're not saying it's just a correlation. They're typically saying we're looking at a partial correlation because they're partialing out maybe other variables that might be confounding, right? That might lead to a misleading conclusion. So what do I want to say here? Except that covariance is useful in that context. That will never be over. You're going to learn that in future classes. But when we talk about relations between variables, covariance by itself. And that's going to be a question on the midterm, I guarantee you. Okay. So when we have two variances, we want to know how to estimate the correlation. Now, this requires you to know what the correlation, how to estimate correlation. Let's see if I can actually, well, I think this is important because in a few cases we're going to have equations that you should know, I would say, because they show that you should have at hand. The math isn't going to be difficult, but the logic is going to be there. So I don't know if I want to do this a la Khan Academy and just like use my terrible penmanship, or if I'm going to try to type out an equation. But if you could say the correlation of x and y is equal to, I'm going to put this in the parenthesis, is the it's the ratio of hold on for a second. Yes. So we want to think about it in terms of standard deviations, right? So we think about this in terms of how do I make this clear? We talk about it in terms of the covariance. Hold on for a second. Yeah, the covariance. Sorry. We talk about it in terms of the covariance of x and y divided by the standard deviation of x times the standard deviation of y. And this is why covariance is interesting vis-a-vis correlation. Because basically what we're doing when we divide something by something else is not typical, not always, but quite often in statistics. We're trying to standardize it. We're taking basically a value that measures association, and we're saying, okay, we want to basically, sorry, my typing is bad. We want to represent it in terms of units that are that transform it given what we know about those units. So we have the association, and then we have it divided by the standard deviation of each. And so we give you the pieces of information here. We have the covariance, the variance of each rather, and from what we know from variance, the standard deviation is just the square root of variance. So technically you want to do, say, the square root of this, and this will even look messy, I apologize, times the square root of this, and then to take that as the numerator, right? So you multiply the product of the two standard deviations, right? What is the standard measure of x and the standard measure of y, and divide it by our measure of association, and then we'll get the correlation. So you should know that. So there are two steps here. I'll say three. First is to recognize that sometimes the information might be made available earlier. Second of all, you would want to recognize what the relevant equations are. So it's useful to have like a short equation sheet, for example, if you want to remember those. And so the way I answer the questions like this is actually, I look at what the question is. I'm very clear about it. Then I'll write down the information. I'll write like variance of Obama vote, for example. I might write in shorthand equals this. Variance of college equals this. And then I'll write out the equation for Obama vote in college. And I typically do that. I write down what I know first. And then that will give you an idea of, well, where's the rest of the information? And this is where I might panic in a test setting. I'll be wondering, oh my gosh, not all information is here because it's not contained. Well, keep in mind, we just asked you a question. Remember, we did this before. I talked about this earlier. We're not going to try to trick you. Trust the system. We talked about the covariance in this question right here. Right, so you take 30.5 divided by 0.5, or the square root of 28.4 times the square root of 88.7, and that's about 0.6. So what you're learning here is you're basically learning about how variance is related to standard deviation, and how standard deviation and variance are both related to correlation, and how correlation is something that is essential to modern statistics, no matter what the discipline is, which is really cool, I think. And so it all builds on each other. So that's the logic, I think, of answering one of those, maybe solve it. We used to call them plug and chug equations, right? But you have to know your inputs, you have to know your outputs. And then it'll ask about this correlation. It's just, I think we'd say it's relatively strong. Notice the answers here are talk about linear relationships because the correlation assumes a linear relationship. So if you're writing this up, you're going to talk about a linear relationship. That's the assumption, and maybe a flawed one. Yes, so when I mentioned he was born in Hawaii, I think he was actually born in Hawaii. I thought he was born in Kansas, but I'm perhaps wrong. He was raised by his grandparents in Hawaii. He was born there. Of course he was born there, because there was this whole debate about his birth certificate, if you recall, by 45. Obama was president 44, and now we have someone who's 45 who would question that. Which is interesting because McCain was actually born in Panama. That's right. He was a U.S. citizen. There's no question about McCain being a U.S. citizen because he was born in Panama. Well, he was born on a military base. Just the fact of the day. This is where context also matters for interpreting things. Often as sanity checks. So when I do data analyses, I almost always show it to somebody. What's going wrong here? Okay. Any other questions that you have? I feel like we're running out of time. I know we didn't address everything, but I hope we addressed the most important. Sure. Someone wanted to keep up with me after this. Any other questions? Anyone else? Otherwise, I will kindly ask how about this? That's a great question. Someone asked, do they roughly cover the same material? Yes and no. So yes, they roughly cover the same material, as long as you know how to set up the code. I'm not going over the answers in Monday. That's the biggest difference. So if we have, oh, don't worry about the midterm. So we have review sections for the midterm. I will have the YouTube, I apologize, I just had to turn it to YouTube. And I'm gonna see what VPN client services there are, because I know China's knocked that off and also makes it more difficult. Russia as well. And I know there are many students who might find that difficult to access. I've been told that. But YouTube is great because you can play videos at double the speed. You can also hopefully get translation, text translation of what I'm talking about. So those will be available for review, and you can read and watch those. But I would say between the two, Thursday section is intended to cover more of the material for the midterm. Monday is more for getting the analysis, syntax coding for finishing the assignments. And I don't give hints, for example, but I do help you sort of analyze make sure you get the data so you can get to the answers. Here, this is more of like, this is the logic of the question here, the concepts covered. That's sort of the logic there. Yeah, so between the two, if you had to pick one, maybe Thursday, but I'd say it doesn't hurt to cover the other one, and I'll tell you why, because as one student had shown, you can flip around the correlation. I learn very well, personally, if I look at the data. I don't know, it's just people learn differently. And for those of you who don't like to hear someone like me drone on and on, I think you check out the speeding up of YouTube videos. That'll be your greatest asset. Also, Mondays are great for those of you working on the final project and you're thinking about, well, how do I run the code? There we go. And that's a different issue. But please contact me. We can meet in person. I've been meeting with lots of students one-on-one. I just talked with, so I think that's it. I'm going to stop here. I'll stop recording. So, and in terms of like, I know I promised Monday, if you were there Monday, I promised, well, we're going to have the advanced R stuff. I spoke with the other teaching staff, and I think that's more of a one-on-one basis, but I'm hoping to start, last year we started after Thanksgiving for the final project, because you do have some time after this to work on the final project. That being said, when I post the YouTube videos, don't feel like you have to watch everything. I'm going to post material that is going to be for the whole course. So if you want to watch, not for the whole course, but probably more advanced or covers stuff that isn't covered yet. So if you want to watch those in advance, good. But it's probably best for those of you who want to rewatch stuff you've already seen. And I also will, I don't think this is an issue, I will also have last year's sections that I've recorded. So if you want to watch these answers played out in a different context, go ahead. I just think the more the merrier. Okay, the only issue I've been having to address with, sorry about that, is the fact that you're paying for this course or you have privileges for this course, so it's technically we're not supposed to share this with the wider community. So that's sort of an intellectual property thing. All right, Finito and Walter, I will. Yeah, those are not yet available under section videos because I need to. You'll actually see that some of the for tonight, some of those videos are going to be disabled because I had to create a new channel. Also for privacy's sake, because one of the things we're having with the YouTube videos is that once you see one, you don't see the others queue up. So I'm trying to make it so that you can get those, you can access those, you can use those in future courses, but also potentially so that I don't get into trouble. We don't get into trouble in terms of intellectual property or basically teaching the course for free. Essentially, I think that's my concern. So. Yeah, but the section video, but that being said, I will link each separate video on the course websites, and then I will link the others. But I'll also give an announcement that says, if you want the videos in one site, bookmark or subscribe to, you know, that I don't know if I can have have you subscribe, but it might behoove you to bookmark like just a video. That way you have one link for all of the videos that I'm providing, not for the others. It's just easier, especially if you're on a mobile device. Okay. And I'm also totally aware that everyone is very busy. You can't watch everything at the same time. So it's nice to have something stop or play at half speed or skip ahead. And we can't do that if you have to go through the Canvas thing. And I should also emphasize there is a Zoom app, right? So I just did that for this class. There's a Zoom app, just go if you're using an iPhone. And there's also a Canvas app. I don't know if everybody uses this, but those are going to be useful, I think, hopefully. And I'll try to make it so that way if you have YouTube on your smartphone. Good. That being said, some people have told me, and I know this was the case with Regan, they've had trouble contacting me through Canvas. I'm not sure what that is. So please, if you have any doubt, email me. And again, there's my number. And if you're getting frustrated and you can't contact me, there's my number. I have to say it is also my cell number or WhatsApp. So if you're out of the country, do that. Otherwise, do that. But text me first if you don't mind, because I get, like everyone else, I get a lot of spam phone messages. So if it's someone I don't know, I won't answer it. But text me and say, hey, I am so-and-so from Stat 100. Can we talk? Typically, I consider myself on call. I'm an academic. We have flexible schedules. So quite often we have meetings, but quite often I can answer your question when you ask it. And the students have made, I feel like there's an imbalance. Students who make use of that really get more out of the class than others, and I want everyone to benefit. So there you go. Thank you very much. We're going to end. Walter, hang on and reconnect in like 30 seconds, okay? Any other questions? Any other questions? Contact me, okay? All right. Cheers. Okay, thank you, Peter. Thank you, everyone.
Hey, Dr. Fossey, am I going to stay on the line or?
Yeah, why don't you stay on the line? I'll just end it and then I'll
okay.
restart it.
Sounds good. All right.
Awesome.